Okay, so we're going to look at special right triangles. Now, special right triangles are triangles that have certain types of relationships where we can actually decipher patterns within their sides and use things other than Pythagorean theorem. You're going to look at special right triangles when we do things such as trig. When you get into pre-cal, you'll do a lot with trigonometry. The unit circle is largely based on 30, 60, 90, and 45, 45, 90 triangles. So we're going to look at the 45, 45, 90 here first in this first video, and then the second video we will look at the 30, 60, 90, or if we have time we may do both in this video and just do basics. So with the 45, 45, 90, these represent the angle measures within the triangle. So if it's a 45, 45, 90, I'm looking at a right triangle whose two acute angles are 45. Now if you remember back when we talked about acute angle, we talked about triangle sum theorem, one of the theorems that we looked at is that the acute angles of a triangle will always be complementary. Complementary meaning add to 90. Because if one angle's 90 and the entire triangle adds to 180, then that means that we have complementary angles for the two small sides, the two smaller angles. I'm trying to rush because I'm running out of battery here. So here is your 45, 45, 90, okay? Now, because the two angles are the same, that means the two sides are the same. So a 45, 45, 90 is actually an isosceles triangle because it's got two congruent sides and it's got two congruent angles. It is also 1/2 of a square. If I were to draw a square and draw a diagonal, that diagonal would create two 45, 45, 90 triangles. So if I were to draw the square here, so I've got my square and I've got my four right angles. Either way I draw a diagonal, I create two 45, 45, 90s. So I'm going to be here, that creates a 45 and a 45, a 45 and a 45. So those are the relationships that you'll see with the 45, 45, 90. Now the 45, 90, 45, 45, 90 has a special relationship. Let's say I label one of these sides, and I'm looking for the perfect color here. Let's say I make this 6. Well, since it's isosceles, if one of the legs is 6, so is the other one. So that's got to be 6. And I want to find the hypotenuse, which is C. Well, there's two ways I can do this. I can take the shortcut or I can use the Pythagorean theorem. So I'm going to use the Pythagorean theorem first. So Pythagorean theorem says in a right triangle, the sum of the squares of the legs equals the square of the hypotenuse. So a squared plus b squared equals c squared. Well, what are a and b in this picture? 6 and 6. So 6 squared plus 6 squared equals c squared. I'm going to go ahead and start working these out as far as trying to get to c. So 6 squared plus 6 squared is 36, not 12, like a lot of us like to think. So 36 plus 36 is c squared, which means 72 is equal to c squared. And once you get down to that point, you take the square root of both sides, because I don't want c squared, I want c. So c is equal to the square root of 72, but I don't want to leave it as square root of 72. I want to simplify the radical. So I'm going to take 72, and I can factor it as 2 times 36. 2 is prime. I'm going to box in the 36 because it's a perfect square. So I can rewrite 72 as the square root of 2 times the square root of 36. Square root of 2 I can't do anything with. Square root of 36 is 6. So I bring the 6 outside, and there's my answer. So that means that my hypotenuse is 6 square roots of 2. Now, if you look at that, if we do this again, let me look at giving you one more example. I'm trying to beat this so that the camera doesn't run out. Let's say this is 10. This is my square and this is 10, and I draw a diagonal, and I want to know what's the hypotenuse here. What's the length of my diagonal? Well, let's do a squared plus b squared equals c squared again. I know they're going to all be 10, so remember each one is a 45, 45, 90. That's a 45, 45, 90, and so is this. So what I'm going to do is I'm going to format this. So I'm going to do a squared. I'm going to imagine I'm just looking at this triangle right here, just this one. 10 squared plus 10 squared equals d squared, which is my diagonal, or you can call it c. 10 squared is 100, so 100 plus 100 equals d squared. So for my next step, I've got 200 equals d squared, and then I'm going to take the square root of both sides. So d is equal to the square root of 200, but I don't want it in that format. I want it simplified. So I'm going to come over and I'm going to take the 200 and I'm going to factor it. It's 2 times 100. 2 is prime. 100 is a perfect square. So I can rewrite square root of 200 as square root of 2 times square root of 100. The square root of 100 is 10, and then I've got square root of 2 left. So it's 10 square root of 2. Now what do you notice here? If the two sides were 6, the hypotenuse was 6 square roots of 2. If the two sides were 10, the hypotenuse was 10 square root of 2. So our simple rule with 45, 45, 90 triangles, and I'll just draw it this way because you can draw them in any direction. When you have a 45, 45, 90 or isosceles right triangle, the relationship of the sides is going to be x and x, because those are the same, right? It's isosceles. And then the hypotenuse is going to be whatever x is times the square root of 2. Now, if we wrote that as a ratio, we would write that as x to x to x square root of 2. That's the ratio of the sides. But what do they all have in common? Well, they all have that x, right? If I were to divide everything in here by x, what would I end up with? Well, x divided by x is 1, 1, square root of 2. So that is your ratio for 45, 45, 90 for all the sides. So for example, if this is 27, that means this is 27 and this would be 27 square root of 2. Okay? Let's try another one. Let's say this is 14. That means this one's 14, and that means this one is 14 square root of 2. So you can hopefully see the pattern. Okay? So that's how we do the 45, 45, 90s. Now if I want to find the hypotenuse, I mean the legs, in these I was given the legs and hypotenuse I found. You can either factor it out or you can take the shortcut and just multiply the leg by square root of 2. But what if we go the opposite way? So I'm going to put a little line here. Let's say I give you a 45, 45, 90 triangle here. And I give you the hypotenuse. Let's say the hypotenuse is 10. And I want to know, what are the legs? Well, what do you know about the legs? They're the same, right? So if one of them, I'm just going to call them something random. I'm going to call them x. If one is x, the other one's got to be x. There's two ways to do this. You can use Pythagorean theorem. So x squared plus x squared equals 10 squared, right? Leg squared plus leg squared equals hypotenuse. 1x squared plus 1x squared is 2x squared, so that becomes 2x squared. 10 squared is 100. And then before I can square root both sides, I want to do just like I would in any other algebraic equation. I'm going to divide both sides by 2. So x squared equals 50. And then I don't want x squared. What do I want? I want x. So I'm going to square root. So x equals the square root of 50. But again, I don't want square root of 50. I want it simplified. So I'm going to take the 50 and factor it. All right? I'm going to do 10 times 5 this time. 5 is prime. Don't have any pairs. 10 is 2 times 5. Those are both prime. So this is another route I can go other than finding if I don't have a perfect square. I'm going to go all prime. So square root of 50 is the same as the square root of 2 times 5 times 5, right? Without a perfect square, you look for a pair. So what I'm going to do is I'm going to circle the pair here. For every pair, one comes out. Because what is 5 times 5? 25. What's the square root of 25? 5. So then I'm left with the square root of 2 underneath. So I've just found the two legs here by going backwards, or by using the Pythagorean theorem. So that's one way to do it. Now what we talked about in class today, remember up here we said that when you have the leg, you multiply by square root of 2 to get the hypotenuse? Well, when you have the hypotenuse, you divide by the square root of 2 to get the legs. So that's another route you can follow. Now remember, I told you in class that every time you have a 45, 45, 90, you can bail yourself out with the Pythagorean theorem. Every time. As long as you're given one of the sides, you can do the Pythagorean theorem. All right? So let's look at this. So instead of being given, for example, 10 and multiplying by square root of 2 to get the hypotenuse, I'm going to divide. So I'm going to do 10 divided by the square root of 2 to get the legs. I'm dividing instead of multiplying because I'm going backwards. To get from leg to hypotenuse, multiply. To get from hypotenuse to leg, divide. If I want to go ahead and write that out, to get from leg to hypotenuse, you multiply by square root of 2. To get from hypotenuse to leg, you divide by square root of 2. But we don't want the square root of 2 in the denominator. We want to rationalize the denominator, which means we want to get that square root out of the denominator. So what we're going to do is we're going to multiply by whatever that square root, that radical is, on the bottom, and whatever we multiply the bottom by, we have to do it on the top to keep the fraction equal. Remember, if you have something like 1/3 plus 2/3 plus 5/6, and you wanted to combine those, you have to find the lowest common denominator, right? Which would be 6. Well, how would I get this to be a denominator of 6? Well, I multiply by 2 over 2, right? What about this one? 2 over 2. This one I'd have to multiply by 2 over 2 as well. So let's multiply across. 10 times square root of 2, I can't multiply what's outside times what's inside. But square root of 2 times square root of 2 is square root of 4, which is what? 2. And then I can reduce. 10 divided by 2 is 5. So you get 5 square root of 2. So, sorry, my kids are in here bothering me. So you got 5 square root of 2 and 5 square root of 2. So that's two different ways that you can solve for the hypotenuse.